In this video, we're going to calculate the instantaneous rate of change for a given function. So to do that, what you need to do is basically take the average rate of change over smaller and smaller intervals until it eventually converges to the instantaneous rate of change for a given value. So the average rate of change formula is given as being change in f, or delta f, where f is your function, over change in x, or delta x, which can be written as f of x1 minus f of x0 divided by x1 minus x0, where x1 is not equal to x0 since we can't divide by 0. So using this formula here, we can calculate the average rate of change over a given interval, which is the difference between x1 and x0, where x0 is our starting value and x1 is the finishing value. So we can use this to find the instantaneous rate of change if we use a small x value near the point on the function that we're trying to find the instantaneous rate of change for. So for example, let's find the instantaneous rate of change for the function y of x is equal to 1 over x plus 2 at the point x equals to 2. Now here's a graph of 1 over x plus 2, which shows it gently sloping down to 0 eventually once it reaches infinity, but that's talk for a later video. Now here's a graph of 1 over x plus 2, so we have an idea of what region we're looking at. We want to find the instantaneous rate of change for here. Think about slope, because that's essentially what the instantaneous rate of change is. So to solve this problem, we will create a function table and calculate the average rate of change for smaller and smaller x intervals. So here's our function table where we have y of 1 is equal to 1 over 1 plus 2, which is 1/3, and y of 2, which is equal to 1 over 2 plus 2, which is 1/4, and y of 3, which is equal to 1 over 3 plus 2, which is equal to 1/5. Now using these values and the average rate of change formula, we can plug in y of 2 and y of 1 and our interval 2 and 1 into the equation and then evaluate it, which gives us 1/4 minus 1/3 over 2 minus 1, which is equal to negative 0.0833. So now we can run the same calculation again on the upper range, and this gives us a finishing value of negative 0.05. So we get a range of negative 0.05 and negative 0.083. So we know that our instantaneous rate of change must lie between those two somewhere, because we're trying to find the instantaneous rate of change exactly at x equal to 2. So we can repeat this process again with a smaller interval step size, and we'll use 2 plus 0.1 and 2 minus 0.1. And using this, we get y of 1.9 and y of 2.1, which comes out to being 1 over 3.9 and 1 over 4.1. And if we plug those both into our average rate of change formulas, we end up coming out with final values of negative 0.0641 and negative 0.06097. So we made a step towards narrowing in our values, because now our high side is negative 0.06097 and our low side is negative 0.0641, whereas before our low side was negative 0.0833 and our high side was negative 0.05. So now to get the instantaneous rate of change, we just keep repeating this process, and so now we'll take an interval size that's really small, so using 2 plus or minus 0.000001, we can get y of 1.999999 and y of 2.000001, which in turn outputs 1 over 3.99, etc., and 1 over 4.00, etc., 1. And if we run those through our average rate of change formula again, we end up coming out with values that are basically the same, of negative 0.0625 and negative 0.0625, which shows that it converges to the instantaneous rate of change. For the value 2, since our input values were small enough in interval size to essentially zero in on the average rate of change for exactly 2, which is instantaneous rate of change. And essentially, you can use this average rate of change with smaller and smaller interval sizes to find the instantaneous rate of change for any function. So this is kind of an introductory step into the concepts behind limits, where you know that a value is eventually going to get so close to another value that you just basically round up and assume that it is that value, which is ultimately what happened here in this case. Is as we took smaller and smaller steps towards being +2 and -2, we eventually got closer and closer and closer to the average rate of change for 2 for our function of 1 over x plus 2. So hopefully that was helpful, and hopefully it made a bit of sense. Thank you for watching.